Okay, I think we've given people enough time. Thanks everyone who's answered the poll, and I imagine that everyone will slowly come, arrive whenever they arrive. I quite liked specifically the person who didn't know whether it was a yes or an also yes. Cool. So for this afternoon, we shall be looking a bit more in depth about like this morning. This morning session is always a bit weird because it's really important to get and explain the basics of LAMMPS, at least as Rui and I understand them, in order to then be able to build up on what was done at the start, so that you can start doing more complicated simulations. And so this afternoon, what we'll be looking at is we'll be delving into the log file and what all of that means. We'll be also looking at some of the more advanced input and output commands that you can use. So some of the compute, some of the fixes, how those interplay with one another. And that'll have a ton of exercises. We've actually, Rui and I spent our lunch making sure that there was going to be a decent exercise for LAMMPS restart files. So we're definitely going to have an exercise for that because there was a question about that in chat. How to output LAMMPS trajectories, how to do all sorts of things like that. Then we'll probably have a break, and after the break we'll talk very briefly about some of the other software that like we'll talk a bit about GPU optimization. Now, unfortunately, ARCHER2 doesn't have GPU nodes or any GPUs at the moment. I think we're due to have 8 at some point, though I'm sure Kevin can tell me if that's wrong. When he joins. What was the other thing? And however, it might be of interest to you, how do you compile with GPUs? How do you run with GPUs? Are some of the tricks to do with that. Rui especially has been running loads with GPUs, so if you've got any GPU optimization or acceleration questions, please do put them in the chat and Rui will be more than happy to answer those. And then we'll finish, we'll also chat about some of the additional packages that people often use with LAMMPS. So how do you visualize your molecular dynamic simulations and things like that. And after that, we'll aim to finish at around, it'll probably be about 4:10 when we finish. We'll talk a bit about some of the other courses that we run as part of the ARCHER2 support team, and some of the, where you can go for additional questions, additional information, that sort of thing. And then Rui and I will probably stick around for a bit if anyone's got any questions that they wanted to ask. We're more than happy to ask things that we didn't end up covering in this course. We might not know the answer, but we'll try our hardest. Okay, so with that, let's get started with LAMMPS log files. So when we finished off, so I've not logged in for the very simple reason that I strongly advise for this session to log in with the -x flag. And what that does is that exports the X11 terminal, which means that you can visualize things on ARCHER2. Now, usually this isn't recommended. It's really usually quite slow to visualize things on a remote server, especially one that's shared like ARCHER2. But in this case, we won't be doing anything too drastically intensive, which means that we'll be able to just get away with it. Now, this is always the scary bit of, do I remember my password? I do remember my password, so this is, that's usually the hardest bit of every course is remembering my password. And then I'm going to go into the work directory because I'm going to be running on the login nodes, compute nodes, 100. Now, one of the things with ARCHER2 is whenever you get an account, whenever you want to get added to a different project, you need a different account name. And I've been added to a lot of projects, and I found one of the easiest ways to do account names is to have the account budget code, so TA100 and then my initials. Cool, so there we go. And I've got a fresh copy of the exercises. So actually what I'll do is I will go back to the second set of exercises and I'm gonna, I guess I don't have to, I'll go to the third exercises and I'm gonna submit the sub.slurm job. While that runs, let me check. I should have maybe checked sub.slurm. While that runs, that's what I want. I'll show you very quickly the input file that we're running. is a copy with minor modifications of the one that Rui was showing you right before lunch. So all of the top bits are the same. The only two differences, probably, are that I've commented out the compute RDF and fix RDF, and I've added a commented out compute MSD and fix MSD. RDF stands for radial distribution function. We'll be talking a bit more about that in the next session. And MSD is the mean squared displacement. We'll be talking also about that a bit more in the next session. But for now, I just wanted to make you aware that we're running the same thing. Oh, there might also be here an output command that we didn't have before, but we'll talk about that again. So that's probably finished. SQ minus me just means show me my SQ for just me. If you do SQ without that, you get to see everything that's currently queuing on the ARCHER2, which you don't want to do. So SQ minus me is kind of the same as SQ minus U user, which outputs just your just the jobs that you're queuing. I've got nothing queuing, which means that my job is finished. So let's look at the log file. Now every log file is the same. Here we've output everything to the same log file, but you can actually separate chunks of your work into different log files, and the way that they'll be printed is up to the point where you've specified a different log file, it'll output everything to the previous one. So here we've only got one log file, so we don't need to worry too much about it. The first thing it does is it tells you everything you've done. So this is just a repeat of my input script. Here it comes across the first LAMMPS command, which is variable density, and it sets the variable density to be equal to 0.8. It'll use that later. We keep going down. It outputs everything, including the comments, which is fine. It helps you. It's useful to remember exactly what you were doing. And here you get to some of the things that you were defined. And here is where we actually call one of the variables. And one of the cool things that you can see in the log files, you can see how LAMMPS deals with variables. And the way it deals with them is here. It has a command lattice, which is going to be a simple cubic lattice, and we're going to put in the variable density into it. And then LAMMPS will automatically replace it with whatever the variable is. In this case, the value is 0.8, so it just replaces it with 0.8. This is quite useful for debugging. If you're using a ton of variables, if you've got a very complicated LAMMPS input file, you can go through the log file to debug to check that all of the variables are what you'd expect they were to be. Then it kind of says, well, okay, we're going to, this is the lattice spacing that we'll have if we've got this density, and that's presumably going to be, that's going to be 1, is it going to be 1 over this cube root of 0.8? I can't remember off the top of my head. Rho equals 1 over v cubed, so 1 over L cubed, so L is going to be equal to, or proportional to 1 over rho to the third. Yeah. It's going to be 1 over rho brackets to the third, which is why it's above 1. Yeah. Then it just keeps going through all of the commands. Whenever LAMMPS does anything, it sort of like tells you what it does exactly. And yeah, this isn't the most exciting bit, but it's a good way of checking that it's doing what you think it is. And then once it gets to the run command, now the run command is the command that tells LAMMPS now we're going to do an MD loop. So we're going to do the entire process that Rui was describing earlier. Where's my mouse? There we go. Where was it? We're going to do this entire process of, well, starting from our positions, we're going to calculate the energy and thereby the forces acting on every particle. From those, we're going to calculate the accelerations and velocities. And from those velocities, we're going to move to a new time step where they're all going to be in a different position. And from that, we're going to calculate all of the energies and forces and just keep repeating over and over again. That's what LAMMPS does whenever we reach a run command. And when a run command happens, LAMMPS tells you, well, okay, we're starting an actual loop bit. Here's what we need to do. And it tells you, well, okay, what are we doing? Here's the neighbor list information. Here's everything that we had in, those couple of neighbor list commands. All of that info is then unpacked into this by LAMMPS, which is quite a fair amount of information. And then it gets running. Now, usually the thing you're interested in a log file is the thermo outputs. If you remember, we defined a thermostyle, which defines what properties we're interested in outputting. So we defined this one as being a custom thermostyle. There are out-of-the-box thermostyles, but usually, I don't know, I've never really used them because they never have all the information I want. And in this case, we are outputting step, i.e. what time step are we on, the temperature, what's the current temperature of the system, the total energy, E total, the potential energy, the kinetic energy, the pressure, the volume, and the density. And we are outputting this every 500 time steps. We define how many time steps we wait between outputting to log file with the thermo command. And so you'll see that every 500 time steps, starting with time step 0, then 500, then 1000, going on, we have every 500 time steps output the system temperature, the total energy, the potential energy, the kinetic energy, the pressure, the volume, and the density. Now, we mentioned earlier, and actually we can check this again, we are running with a fixed NVT, which means the number of particles is fixed, the volume is fixed, and the temperature is fixed. And so you'll notice that the volume is indeed fixed. Because the number of particles is fixed, that means the density is also fixed. The temperature doesn't look quite as fixed. And that's okay, actually, because we've been using a thermostat. So we're using the default is the Nose-Hoover thermostat in order to control the temperature. And temperature naturally fluctuates. It's one of the things about molecular dynamics is that you're running a discretized representation of a continuous the continuous movement of particles. So what does that mean? Well, you're effectively saying, well, we're sort of doing snapshot by snapshot by snapshot. And because of that, you get non-physical things like potentially energy losses or gains when you shouldn't have those, which wouldn't happen if you were running a system with like a system continuously rather than discretely with the delta t time step that we've been using. Now, usually the amount of gains or loss that you get in this way are very small, especially if you've chosen the correct and appropriate time steps. They should be really small, but just to make sure that we're not just losing energy, because a really small change, if you're doing something millions of times, is still going to start being noticeable. We ensure that the temperature remains fixed, or we try to keep the temperature to get the temperature to remain fixed by using a thermostat. What that represents is an external heat bath that ensures that our simulation box keeps the same sort of energy, same sort of temperature as the external heat bath. And that's why the energy fluctuates. Now, while there are fluctuations, the average temperature should always be 1. And if you look, actually, yeah, it's sort of like zeros for a bit, then a bit above 1 for a bit, and it kind of fluctuates over and over again. Now, the other points of interest, the other things to think about is when we set up our simulation box, we used the simple cubic structure. And so what we did when setting up our simulation is we said, okay, we're going to have a box. It's going to be a cubic box. It's going to be, if we go back up a bit, where is it? There it is. It's going to have 0. It's going to have 0 axes. They'll start at 0 and go all the way to 10 along the x-axis, 0 to 10 along the y-axis, 0 to 10 along the z-axis. And at every single integer point of this box, we're going to put an atom. So if we're running a box with 0 to 10, 0 to 10, 0 to 10, we're going to end up with 10 cubed because of the way things wrap around. You actually only put an atom either on 0 or on 10. So we're going to end up with 10 cubed or 1,000 atoms in total. But they will be spread exactly evenly in a simple cubic crystal structure. Now, this is not very physical, this is not very realistic, and one of the first things that will happen when we run our simulation is because we've given the particles a small energy kick using the velocity command, they're all going to start to move, and the energy should reduce as the energy will reduce as the system equilibrates and tends towards the lowest, the minimum energy that it can achieve. That's thermodynamics. And so if you look, the energy starts at 3.86, and if we go all the way to the bottom of our simulation, it finishes at 3.78. So it's reducing slowly over time. And this reduction happens along both types of energy. So the potential energy, 5.36, reduces to about 5.21. And the kinetic energy, which is directly related to the temperature, should not reduce. And indeed, it's at about 1.5 at the top. And it's actually quite low at the bottom. That's interesting, which probably indicates that our thermostat damping is too long, or it indicates that we're using too short a time step. So I noticed there's a question in the chat: how high can the values fluctuate to still be considered acceptable for temperature and pressure in the NPT ensemble? I mean, fluctuations always happen. So you kind of you need fluctuations in your system, because the alternative, if you don't allow your temperature and your pressure to fluctuate in an NPT ensemble, fixed number of particles, pressure, and temperature, if you don't allow those properties to fluctuate, then you are restricting your system much too much, which means that you might end up simulating something which isn't very physical. Effectively, what you're saying, like just naturally, in any physical system, there's going to be fluctuations in energy and temperature. Like at the moment, the room I'm in is probably around 22 degrees. That doesn't mean that every single angstrom by angstrom by angstrom box, or even like 100 angstrom by 100 angstrom by 100 angstrom box, is going to be exactly 22 degrees. And you've got to bear in mind that we are simulating one of those boxes of that size. And so there's going to be natural fluctuations anyways. Now, how big is it kind of depends on what you're trying to simulate. If if you're looking at something like a reaction and you need something to be quite precise, you don't want fluctuations to be more or less than 5 degrees C. If you're using real units or SI units, I think it's Kelvin in both anyways, but you know what I mean. You don't want a greater fluctuation than plus or minus 5K. Usually, and Rui can correct me because he's been doing this more recently than me, but usually you want your fluctuation to be no more than about 2.5 Kelvin either way. Is that about right, Rui?
So I've not done a lot of reaction stuff. Most of the stuff I've done was like physical absorption or aggregation or anything like that. But yes, we tend to try and on our production runs to stay within that 5K band around your target. If your system is more sensitive to it, I guess you might want to have to dial that in. The stuff I was doing was mostly room temperature, so it wasn't a massive. The difference, 5 degrees either way, wasn't massive to the effect that we were seeing. So we weren't as picky about that. But in certain circumstances, it can be.
Cool, thanks, Rui. I think most of my stuff also didn't matter too much, but yeah, I mean, basically the damping parameter is what gives you the option of is what controls how large or how frequent those fluctuations are. Cool. And then at the foot of the log file, you get the information we've already looked at before. You get the loop time, which tells you how much time you've spent on this specific run command. So if I were to add an extra run command, it would give me 2 loop times, and I might actually do that just to show an example. It tells you how many processors you've been using, how many time steps you've done, and how many atoms you've been running with. And then it tells you the performance. We've already looked a bit at the performance information. You'll notice that the amount of different sections that I'm getting here is smaller than the amount that we were getting for the ethanol simulation. And part of the reason for that is that we're only getting performance information for the bits we've used. So this is a simple uncharged Lennard-Jones system. We don't have any charges. We don't have any bonds. We don't have any angles. So the bond calculation time and the k-space calculation time are not here because we don't use them. And then it tells us, all of the information that we've been looking at before. So it tells us what is the minimum time that any processor was spending on calculating pair. On calculating pair interactions. So particle-particle and pairwise interactions. What's the average time? What's the maximum time? And what's the percent difference between, how much more work is the processor or core that's doing the most work doing in comparison to the one that's doing the least amount of work. And in this case, it's 5%. It's and it's averaged as well. So it's averaged per time step rather than being this absolute maximum divided by this absolute minimum. The 5% is actually pretty good. So pair tells you the information about the pairwise particle interactions. So in this case, it's the Lennard-Jones interactions, but if you were using, say, discrete element methods, you don't use Lennard-Jones. Instead, you use frictional particles, and it'll tell you about that specific interaction. The NA tells you how much time you're spending on calculating neighbor lists. You usually want that to be low. Comms tells you the amount of time you're spending in communication between cores. So there was a question before lunch about how many particles do you want on a per core on average. Well, here we run a system on 128 processors. That has about 1,000 atoms, so 1,000 particles, which means we're on a bit less than I don't know. We're probably on about 8.5 atoms per core, and most of our time, in fact, 3/4 of our simulation time is spent in communications. It's spent in cores talking to one another, saying, "Oh, you should be holding on to this particle now," or "Hey, can I have this particle because it's in my bit of the region now?" That sort of thing. This number here is atrocious, and if I was doing anything other than wanting a quick simulation that runs in under 10 seconds because I'm doing a course, I would either make my system bigger or I would reduce the number of cores that I was using. But yeah, at the moment we're dominated in communications, which means that we're wasting most of our time. You usually want this to be maybe somewhere between 10 and 20%. Ideally, you want most of your time, the vast majority of your time, to be spent in pair. Output is I/O. You probably don't want that to be much more than 5 to 10%. Modify is any of the fixes, it's any of the compute, it's all of those things. And other is anything that we've not talked about yet. Here it also gives you a ton of nice information about, there it is, this is all to do with neighbor lists. And it tells you how many total neighbor lists were built, what's the average number of neighbors per atom. So it's 91 neighbors per atom. So going back to the question we had before, you probably want, because of the way things operate, you're probably wanting to have roughly the same number of particles per core as you have average atoms per neighbor list. So if we've got roughly 91, let's call it 100 atoms per core in this case, or particles per core, we'll probably be performing a lot more efficiently, and this will reduce significantly. The neighbor list was built this many times, and there was this many dangerous builds. What does a dangerous build mean? It means that it's if not all of the atoms are on a given core, then you get a dangerous build. And in this case, there's no way that most of the atoms are going to be on a given core, given that there's eight particles per core, and there are 90 particles per. So there's 10 times more particles in the neighbor list than there are per core. Yeah. And then it tells you at the end we wrote a restart file, which we'll be looking at in a sec, and it tells you the total wall time of around 6 seconds. So that was a quick run through of the log file and how to interpret it. At this point, does anyone want me to? I know I went through this very, very quickly. I'm happy to focus a bit more on any specific part or to answer some questions on it. One thing I would say is if you Google LAMMPS thermostyle to find the LAMMPS manual page. Let me zoom in a bit. One of the great things it tells you is it tells you every possible argument that you can have, for instance, if you use custom. And custom is the one I tend to use. So you can have things like step, you can have elapsed, which is the elapsed wall time. You can have, I think, is that right? Elapsed is time steps since the start of the run. You can have time, which is the simulation wall time. You can have CPU time. You can have van der Waals energy if you're doing long-range interactions. You can have dihedral energy. You can split up all of your bond energies into like bonds, angles, dihedrals, improper bonds. You can output volume, density, the box boundaries. Those won't change at all, so that would be quite boring in this one, but that's absolutely fine. And you can also output, we'll talk about these in a sec, but you can output things that are called, that you've defined, user-defined variables with the v underscore name of the variable, and computes with the c underscore name of the variable, and also f underscore will tell you, let you output some of the values in a fix. So what does that mean? And actually, there's a couple of things I wanted to show real quick. So let's remove slurm, restart, nvt log. Don't want to remove in.lj exercise. What does that look like? Oh, that's better. In.lj exercise. And I'm going to add c underscore density. Now what I'm doing here is, oh, I don't want it there. I want it here. C underscore density. Now what I'm doing here is, you remember how we've got this variable here at the top called density that we've set equal to 0.8. Well, I'm now going to try to output it in my thermostyle. And the other thing I wanted to do as well is to do, if I do log dot new output run 50,000. So this will take about 30 seconds to run, if you just bear with me. I'm happy to answer any questions that anyone has while waiting for this to run, or even if it takes a bit longer. So please do let me know your questions. Oh, that took less time than I thought. Probably something didn't work. Yeah, something definitely didn't work. Ah, there we go. It's because it's a variable. Silly. Yep, so log files are also super useful whenever you do anything wrong. It tells you exactly what LAMMPS didn't understand. In this case, it couldn't find the thermo compute ID. And it tells you what was the last command that it did. And yeah, that one is definitely my mistake. Slurm log. Cool. Where is it? That should be a V. So V for variable, C for compute, F for fix. And because here we defined it as a variable, it should be V underscore. And now, famous last words, but it should work. Oh, still hasn't. What's it I'm happy with now? T. I doubt it's this, but one last go, and if this doesn't work, we can just say that it was a valiant failure. Slow there. Now, this may work. If it does, that would be louder. Interesting. at least this crashes quickly. And again, this is why when you're doing tests and wanting to find out, like, it's always worth running a very small test just to make sure that everything's doing the things you expect it to, the way you expect them to, and hey, it's gone 3 seconds further than last time, so this is probably working TM. But always do tests that are short and that are not very costly computationally to make sure that everything's happening the way you want it to. Cool. So now you'll notice instead of having just one log file, I've got a log.start whatever, and then a log.new output. If I look at log.start, and if I go to the end of it, it still gives me all of that breakdown information from before, but then it says, oh, and now you've moved to a new output, which is called log.new output, and all of the future information is in there. Now, the other thing that we've got in here is, let's make that a bit bigger that way. It just won't be happy. Fine. The other thing that we've got in here is that's why our v underscore density outputs our density, which is still 0.8. But this is mainly to emphasize that if you can set a variable, in fact, you can set a variable which is maybe even dependent on things like temperature or pressure or things like that, and output it every so often to get an idea of how that value is changing over time, which can be really, really useful if you're trying to get certain scientific information out of LAMMPS. In terms of the restrictions on variables, you can do loads with variables. You can define variables as equals, which is what we've done, and you can use things like mathematical functions, group functions, region functions, any of the thermostyles, so you can use like volume, kinetic energy, pressure, whatever. There's some special functions. You've also got like other ones. We'll be talking about loops a bit later, or indices a bit later, which let you do things in a repeated fashion so that you can change things one at a time. And yeah, like there are a lot of examples in the LAMMPS manual. I'm not going to go through all of them, not least of which because I'm overrunning a bit. But yeah, just be aware that they're there. Cool. And the other thing I wanted to show is if we do log.new output, well, it starts exactly where the last run left off. And because I've not changed anything, it's doing exactly the same simulation, just a bit longer. And at the end, it outputs all of that information as well. So it tells you what the total log time is, as well as for this specific section of the code, what is the MPI task breakdown. Okay, let's check that I've not missed any. Oops. And do let me know your questions, by the way. I'm more than happy to answer them. Yeah, we've talked about that. We've talked about that. We've talked about the performance. Yeah, so there are 8 possible MPI tasks. You can have pairs, which is any non-bonded interactions. So in this case, van der Waals. Bonds, which includes all bonded interactions, so angles, dihedrals, impropers, also bonds. K-space is long-ranged interactions, EWAL, PM. I'm not quite sure what MSM is, but apparently that one as well. NA is construction of neighbor list. COM is communication time, so parallelization overheads. Output is I/O, input-output times. Modify is fixes and computes, and others everything else. And here we've got the rule of thumbs. You want most of your time to be in pair. Neighbor, you probably don't even want to be up to 30%. You probably want that at like 15, 20. K-space, K-space can usually take a while, but you probably don't want it much more than 25%. And COM is you want it to be as low as possible. Yeah. Great. So next section. Now we're going to start playing around with LAMMPS a bit more. And we're going to look at some of the things that we can tweak within our LAMMPS submission script in order to get some additional physical outputs that are maybe a bit more complicated than just what the temperature of the system is. One thing I will say about this is we've chosen some rather simple case studies for this. What we're trying to get across is more how you would go about doing something like this and where you can find the information rather than telling you about all of the possible ways of doing this. The main thing we'll be focusing on is going to be LAMMPS fixes and LAMMPS compute files. So there we go. LAMMPS has a ton of potential fix commands. MSM is multi-level summation method. Cool. I'm sure you can explain to me what that is later, because that sounds quite cool. LAMMPS has a ton of fixes, and some of them are just variations on each other. So for instance, fix average correlate is probably going to be very similar to fix average correlate long. But there are tons and tons of them. Look, we're still not there. Someone mentioned Langevin earlier before. That's if you want to use the Langevin thermostat, it's all there. But yeah, I think there's about 150 to 200 last we checked. Something like that. There's loads of fixes, and they let you do loads of things. Like, for instance, do you want to have a magical wall through which particles can't go? Well, you can fix a wall in the middle of your simulation box, and that's absolutely fine. You usually need those if you want a finite-sized box, so not something that's got periodic boundary conditions everywhere. Do you want to fix the viscosity of your system? You can definitely do that. Do you want to fix the temperature of your system? There's loads of ways of doing that. Do you want to fix some of the bonds in your systems? You can use the fix rigid. There's also the fix shake if you're looking specifically for water. I think that's in there somewhere, isn't it? Yeah, there it is, fix shake. And rattle, also for water. Both of those are for water. Phonons, if you're playing with phonons, we're definitely not today, but it is an option. And then some of them we've already seen before, like a fix MBT command. Someone spoke before about the MPE command, which we'll be playing around with, MPT command, which we'll be playing around with in a bit, and things like that. So there's tons of fixes, and there are also a lot of computes. Yeah. So those are going to be the main focus of this session now. Now, admittedly, I say that, and then the first thing we're going to talk about is actually LAMMPS trajectory files. So what is a LAMMPS trajectory file, and why do we want one? I have output. This might go horribly wrong, but we'll try it. Oh, cool, that didn't go too bad. In my LAMMPS input script, I had this command here, dump, and dump modify. Let's start with dump because that's the one that's more interesting. What that does is that'll output the properties of each individual particle in your system every so often. So in this case, we've called our dump just 1. We could have given it any name that we wanted. We could have given it, I don't know, trash output, for instance, maybe trash output rather than Raj output. And that would have worked just as well. It's whatever name works for you. When you've only got one, or when I've only got one, I tend to just use 1 as the name because it's simpler, but yeah, you can use whatever you want. Here you define which group of atoms, which set or subset of atoms you're going to be outputting this information for. In this case, we want to output it for all of our atoms, but we could have created groups earlier in our file and only output it for some of the atoms if we wanted. What type of dump LAMMPS trajectory are you going to be building? It's going to be a custom one. We're going to be outputting it every 100 time steps to the file called nvt.lamps trajectory. And we are going to be outputting for every single particle their ID, their type, their x, y, and z positions, and their velocities in the x, y, and z position. And now the dump modify, all that does in this case is you name the dump file, you name the dump command that you want to modify. In this case, it's trash.output, trash_output, and then you say what you're going to do. So in this case, we're going to sort it by IDs. And so our final output file, the nvt.lamps trajectory, is going to be a file that contains all of the particle positions and all of the particle velocities, as well as their ID and their type. That will be output every 100 time steps, and it will then be done. It will be output in such a way as the particle with the lowest ID is going to be at the top, then the next lowest, and the next lowest, all the way to the highest ID. Yeah. And if we look at the output file, we see that for time step 0, So then, yeah, the LAMMPS kind of in the LAMMPS trajectory, LAMMPS outputs. Okay, well, the first thing we output is the time step. The time step is 0. Next, we output the number of atoms. There are 1,000 atoms. Then we output what are the box boundaries, and bear in mind that it's periodic, periodic, periodic in both x, y, in all of x, y, and z. And it uses scientific notation, which is interesting. That wasn't always the case, but it is now. So it goes from 0, 0, 0 all the way to 10.77, 10.77, 10.77, which is what we expected from when we looked at our log file. And then here it says, okay, and for this time step, we're now outputting for every single atom, we're outputting their ID, their type, their XYZ position, their velocity in the XYZ position. And so at time step 0, 0, 0, they should all be in a perfect grid structure. And here it is, you've got atom 1 is there, then, you know, there's its position, and there's its velocities, which have been randomly determined and assigned with the velocity command, and then here's atom 2, all the way up to atom 1000. We'll get to it. There we go. And once we get to atom 1000, the next thing we see is, well, okay, we've been told to add the position every 100 time steps for all of these atoms. So here we are, add a new time step. This is the time step number. This is the number of atoms at this point. The reason it says the number of atoms is that sometimes you can have simulations where you gain or lose atoms. In this case, we shouldn't. And here's the new box boundaries. This can be interesting if you're running in, say, something that allows volume fluctuations. So if you're fixing your pressure, for instance. And here are the new positions. So you can see that, for instance, atom 1, which was on 0, 0, 0, is now on 0.57, 10.69, and 10.72. So it's sort of shifted a bit. And it keeps outputting this. Yeah, so there we go for like time step 300. Yeah, it keeps outputting this over and over again. Let me quickly go back to here if we. So I've only output a couple of things that are usually useful for visualizing your simulation, but there are a ton of ways that you can, ton of definitions that you can have for your dump command. Again, this is one of the ones where I usually use custom, mainly because you've got a lot of control over what you do, but there are some out-of-the-box ones. So yeah, so here it tells you like, well, here are some of the attributes that you can use when you're using custom or whatever, and you know, you can have ID, molecule, you can have which processor it's currently on, you can have, I think that's right, yeah, ID of the processor that owns the item, ID plus 1 of the processor that owns the atom, just in case you're worried about the, you know, starting from 0, starting from 1. Things like the unscaled atom coordinates, the scaled atom coordinates, so that sort of like reduces everything as if the simulation box was a 1 by 1 by 1 box. Unwrapped, so when an atom leaves from a periodic boundary, leaves through one of the boundaries, a exact replica that enters from the opposite side of the box. With the unwrapped, it doesn't tell you where it is within the box, but it tells you how far the atoms traveled in total. You can have things like orientation of dipole moments if you're using dipole particles. You can have things like the angular velocities. You can have torques, and you can also output like compute command outputs, variables, force fixes for individual atoms. So there's loads of things that you can do. And in a similar vein, there are loads of things that you can do with dump modify, such as append. You can restart a run and just append to the same file. You can balance, I'm not quite sure what that is. You can, yeah, but again, for all of these, you can look through, yeah, you can look through the actual manual, and it explains in quite verbose text exactly what everything does. All this to say, there's loads of different things that you can play around with, and there's loads of information for you to check. Usually, if there's something you want to do, LAMMPS probably knows how to do it. Now, why would you care about running this sort of thing? I'm actually going to steal a bit from the next session, but why do you want an output trajectory? And why did we call it LAMMPS TRJ? LAMMPS TRJ is a specific name. The reason we've gone for this is because it's recognizable by programs that play with LAMMPS quite well. One of which that we'll use right now is one called VMD, which is Visual Molecular Dynamics. And with that, you can input a LAMMPS trajectory file. And it should, hopefully, if I've not messed anything up, it should load it up. And then you can look at the trajectory. Now here you'll see one of the big reasons why I strongly recommend not doing visualization on remote systems, namely, it can take a while to get anything done. I don't think you're able to see this. Now you're able to see that's the simulation box. And that's the little, so let's make this a bit nicer. By going with van der Waals, 4.5. Let's also there we go. So now we can see the box, and if we go, let's run backwards. Let's just go back to the start. There we go. You know how I said at the very start that our simulation is a perfect grid of particles. Let's reduce the size a bit. Here is our perfect grid of particles at the start of our simulation. And then we can press play, and it shows us a frame by frame. So here we're on frame 30 that's been output to the LAMMPS trajectory file. So 30 is going to be time step 2900, so 2900. This is what the simulation looks like. And you can play around with things. Now, in this case, it's a Lennard-Jones fluid, so there's not really anything exciting happening. But you can imagine that if you're looking at maybe, I don't know, surfactants depositing on a surface or something like that, having a nice, easy visualization thing to visualize your system with is usually very helpful. It also is always a good idea to look at your system and what it's doing to make sure that it's doing what you expect it to do. So that's one of the uses of a trajectory file. Another potential use for it is, let's pretend for whatever reason, let's pretend that you forgot to output something. What you can do is you can use a LAMMPS rerun command. So here we've got a LAMMPS rerun command, which is, it's got all of the same information at the start as our previous command. So we're defining things like what's our unit size, what's our lattice size, what's our, what's our interactions, how often do we update neighbor lists, what fixes are we using, and then like velocity, time step, thermo. But here all I've done is I've added or uncommented this compute RDF. And now with this command, I'm able to, instead of running an entire new simulation, I can read my trajectory file. And I'm telling LAMMPS, rerun this trajectory file. It's a LAMMPS dump file, which has X, Y, Z positions and Vx, Vy, Vz velocities. And calculate all of the things that I've asked for based on this. And you can also like add things to the thermostyle as well, or things like that. So it saves you having to rerun a simulation if you realize at the end, I forgot to add this, that, or the other. And if we that, hopefully that'll work. I have edited a bit the original exercise file, so it might not be happy. And if it isn't, we can just rerun it. It's fine. And yeah, basically what it does is it just reruns your simulation. It reads in all of the every single frame that you've input, and it does whatever calculations you've asked it to do. And now, hopefully, if I've not made any mistakes, there should be a file called RDF, and it should be non-empty. Perfect. Cool. And so, yeah, you're able to create these, create new outputs that you'd forgotten, or without having to maybe spend hours rerunning something, or days sometimes. So let's talk a bit more about what we're doing with the RDF command, because I kind of started this session off by saying, oh, we're mainly going to be talking about computes and fixes, and then I proceeded to not mention a single computer fix. So what are we doing here? We are computing the RDF, the radial distribution function of our system. And the radial distribution function, it's basically, Rui phrased it brilliantly in the notes. Where is it? Yeah, the radial distribution function, it describes how the density of particles varies as a function of the distance relative to a reference particle. And then we compare that to what the density would be like if it was a perfectly uniform, if there was a perfectly uniform density. So basically, as your radial distribution function should always tend to 1 as your radius tends to infinity. And it sort of tells you roughly, is there a structure at all? Is there any signs of structure to your current system? And so here, the way we've done our compute command, all compute commands are the same. The first couple of steps are always the same. The first thing you do is you call the compute command with compute. You give it a name. So just like we gave a name to the dump file, to the dump command, or we gave a name to the fixes, or all of those things. You give it a name. You define which group of atoms you're computing something for. In this case, it's all of them. And then you name the compute. In this case, it's RDF. Now, once you've named your compute, everything after that can vary because it depends from compute to compute. In this case, the things that it's interested in are how many bins are you using your RDF over? What is the maximum distance cutoff from your RDF? And this is your maximum distance. So here we've said that we want a maximum distance cutoff of 3.5, which means that we want to cut off our radial distribution function and stop calculating it for anything that is greater than 3.5 length atom diameters away from the representative atoms. And we're going to split that space into 150 bins of equal size. Yeah. Now, a compute command in and of itself doesn't do anything. It will not compute something in the background, and it will only compute something when it's called. And so that's why for the RDF, because it's something that we want to average over the entire of the simulation time in order to get it to be more smooth and get a better understanding of our full system. It's why for the RDF, we need to have a fix command that calls it. And this fix command, we've just called RDF output. It's for all particles, and we're going to average over time for all particles the RDF that we're computing. Yeah, we are going to output it to a file called RDF _lj.out, and we are using the vector mode for this. I can't remember if we described what the vector mode is. We don't. Mode vector. This fixes. So with mode vector, we're effectively saying what's going to be output is going to be a vector rather than a scalar. So we're defining the type of output we're expecting. And then finally, this one's probably one of the hardest bits to get your mind across. These three commands tell you, I never remember the order, to be honest. The first one is the frequency at which you will be checking this output. So every 100 time steps, we're going to compute the RDF. The second time is the number of times we're going to repeat this. So we're going to repeat this 500 times. And then the third time is how many total time steps are we going to do this over? So we're going to do this over 50,000 time steps. So what does that mean? Well, that means we're going to, every 100 time steps for 500 times for the 50,000 first time steps of the simulation, we're going to compute the RDF. And we're going to average all of those together into a single final radial distribution function that we're going to output to the file rdf_lj.out. Yeah. So if we look at the file rdf_lj.out, what have we got output? Well, it tells us we've run this over 50,000 time steps. We have 150 bins, and the first one is number 1, the last one is 150, and then by construct it'll tell us which bin number is this, what is the midpoint of this bin. So the midpoint of bin number 1 is going to be at 0.01116667, then it's going to be 0.035, then 58, etc. Then here it's going to tell us, here it tells us, I think it's, I can never remember which one 3 or 4. I think 3 is what is the radial distribution function. I never remember what 4 is. So let's output it and find out. So a good way to plot things is to use the GNU plot module, which lets you use GNU plot. And we're going to plot rdf lj.out using 2 because I want to use the bin sizes, 3 with ls with lines and points. Line size is going to be 2, point size is going to be 1.5, and so here it shows us our radial distribution function. And it shows us, what does it show us? Well, it shows us that as before a distance of 1 sigma, so before the distance of 1 atom diameter, the probability of finding something in a distance less than 1 diameter away is going to be very close to 0. Okay, cool. The final one is coordination number, which I'll show you. Then, when we're at around, call it 1, maybe a bit more than 1, we've got a super high probability relative to an average density of 0 of finding a particle there. Then it sort of dies off a bit, then it increases again, then dies off and increases. But this shows us our radial distribution function. And if we do 4 instead, what this shows us is it's the integral of the radial distribution function. And so at around 1, it suddenly goes up a lot, and then it sort of dies down, then it goes up again and dies down, and then just goes up linearly. We're tending towards linearity. Cool. So at this point, there's a question. Is there a good definition for what a compute and what a fix is? Things that you have to have for a simulation to take place in addition to things like the RDF. Is there a good definition? So a compute is something that you want LAMMPS to work out what it is for you and output when it is called. A fix is something that you want LAMMPS to have set within the simulation and do either once or on a regular basis. But it sort of depends. So I guess the difference is you can have a compute and it might not do anything for the entire simulation. But a fix is an extra set of instructions that LAMMPS will carry out during the simulation. Does that make sense? I'm getting no answer, so probably not. Where's the mouse gone? This one is. So an integrator has to be a fix. Yes, that's right. Yeah, your time integrator would have to be a fix. And indeed it is. So in our current setup, our integrator is int.lj exercise. Our time integrator is defined when we fix NVT. And then we can actually change sort of the run style that we're doing, but the time integrator is this, and if we remove this, actually nothing's going to happen in the sense of the simulation just. I'm always happy to break simulations. Like basically none of the atoms will move if we do this. Sorry, it'll take about 30 seconds to get through not doing anything, but you know, it's always nice to show these things. So fixes are instructions that LAMMPS must carry out, whereas computes are instructions that LAMMPS will carry out when it's asked about them. And let's just PMD T. Black Box and Doom. I'm not even going to bother to, actually no, I might as well just to emphasize the point. So the only difference between this run and the previous one is that I've, like we were agreed, the only thing I've changed is I've removed a fix, right? I've commented out a fix. And now, this is what my simulation looks like. You'll notice this number is going up. But yeah, nothing's happening in my simulation. It's all the same simulation. Because there's no time integration, because there's no fix, because there's nothing to tell LAMMPS that it needs to do something. Cool. I'm going to quickly rerun that because I kind of wanted that output for something else. No, that's wrong one. And while that's running, cool. So one of the questions is how can the local density be computed? So one of the things that you can do, you know how we've been using for everything, we've been using all as our group. So whenever we're dumping trajectories, it's trajectories for all atoms or for all particles, or when we're computing the RDF, it's for all particles, or when we're looking at the MSD, or when we will look at the MSD, it's for all particles. One thing that you can do is you can define groups. So LAMMPS group. And you can define a group to be a region. And so if you wanted to find out a local density, probably the first way to do it is to say, well, let's split my simulation into regions and output the density for each region. Does that make sense? Cool. Excellent. So we've done the radial distribution function, and we're about to get to a break. So actually, just before the break, and during the break if you want to as well, I'll pose this exercise. I'm aware that this feels like we're running a bit overly long for this exercise, but actually we've done more than, we've done a fair amount of this. I just didn't end up coding in the same way as this page is set out. But yeah, so before and during the break, I would recommend if you go into exercises and you go into 3 advanced inputs exercise, have a play around looking at the in.lj.exercise. You know how we set the variable density at the start. Uncomment the couple of lines for the RDF, and then have a play around to see how the RDF changes as you change the density. So what happens if you run the simulation with a density of 1.2 instead of 0.8, or if you run a simulation with a density of 0.1 or even lower than that rather than 0.8. And when we come back from the break, we can talk about the solution and what this means. Cool. I'll be around if anyone has any questions, and I'll be happy to answer them. Otherwise, I think the break is meant to be until, well, that's a long break. Yeah, so I guess it's meant to be until about 22. And after that, we'll just finish the course and in that last session. Yeah. Please do let me know if you have any questions. Please let me know if you've got any problems running any of the jobs or simulations or you're not getting effect. Otherwise, I will see all of you. I'll still be around, so do ask me questions, but otherwise I'll see all of you at 22:04 UK time, so in about 35 minutes. Okay, let's get started. So, just a quick question, hands up, did anyone do the exercise? I mean, I did, but did anyone else? The silence is deafening. Cool. So, I did do the exercise. Probably the easiest way to do it is to edit in.lj.exercise. And if you go at the bottom, uncomment the compute RDF, fix RDF. And then at the top, you can change the variable density to be whatever density you're interested in. And then you can run it 3 times, once with each density. When you've done that, you can plot the results. I'm using GNU plot here to have a look at what the final radial distributions look like. And actually, this answers one of the questions that was in the chat right before the break or during the break, which is how can you tell what phase something is in when it's in a liquid or whatever? One of the ways that you can look at that is by looking at the radial distribution function, which gives you an idea of roughly what sort of structure you're in. Now, the reason that I suggested the 3 densities that I suggested is because we've been running at a density, a reduced Lennard-Jones density of 0.8. And at that state, the Lennard-Jones system is a fluid, it's a liquid. And the 0.8 version has this lovely, it's the green curve. I don't know if you can see that. Probably make that a bit bigger. There we go, that's a bit more visible. It's the green curve there. And it's got this sort of like nice, smooth up and down wavy motion. Now, if you increase your density, your reduced density to 1.2, which is the highest bound that I suggested, you end up getting this thing where you've got a super high peak, especially in comparison to before when you were fluid, and then it sort of goes down to super low, and you've got very defined peak and repeating patterns and things like that. And the reason for this is at that density, your system is it's a solid. So you form a crystal, and this radial distribution function with this very set high peaks, low peaks, repeated structures, that's standard of a solid. And then finally, at the lower density, actually, I'm pretty sure that the lower density of 0.1 or 0.01 is still too high to, it's not quite a gas at that point. So I've actually reduced mine to 0.025. And yeah, you get a telltale sign of you get a peak and then a sort of exponential like decay towards 1, which is indicative of gas. And so the reason that I suggested looking at those 3 radial distribution functions is so that you can see all 3 phases that a Lennard-Jones fluid can take, liquid, gas, and solid, and see what their radial distributions look like. Which I think is just what the solution says. There's a small point for those of you who are interested or who use YAML. It is possible to output something as a YAML in YAML format by just putting .yaml at the end. So if instead of using rdf_lj.out, we'd use .yaml, we would have had a YAML file instead. Cool. So now what we're going to do is we are going to talk about restart files, about mean squared displacements, and then we'll move on to the final session for today. So one of the things that we generated when doing these runs, well, I've been running a lot, is we've generated restart files. So here we've got a restart.lj equal, and There were some questions about, well, how do you use restart files? So let's look at int.lj exercise. The way I've set my restart file is I've just put a write restart at the very end of my simulation, and that outputs it. And the restart file is it's a binary, so it looks like nothing. But it's a binary file that stores all of your particle, a lot of information about your system. So it stores the particle positions, the velocities, but there's a lot of things that it doesn't store. So it doesn't store things like, it doesn't store things like fixes or computes, variables, regions, neighbor lists. They all start from scratch rather than they need to be recomputed. Anything which is like case-based styles and any modifiers you've added, all of those things are not stored within a restart file. So you need to redefine a fair amount of things if you want to start from a restart file. And that's what we did in in.lj.restart. We basically got the first command is the read restart. And you'll notice actually this first command, after that command, the commands that we're calling, we called before in our in.lj_exercise file. But we've skipped a ton of them. The next command after reading the restart is the linear momentum command, which doesn't happen until we don't need to define any of the atom types, things like that, or things like that. We can just skip straight to there, and only upload the things afterwards. So yeah, we kind of define what we want to fix. We want to fix the linear momentum, and we want the linear angular momentum to be fixed. And here we're going to, let's say we want to restart and we want to run in NPT, so fixed number of particles, pressure, and temperature, rather than NPT we used before. Yeah, we can do that by just changing our fix command. We've defined our time step, thermo style dump. Again, we're dumping to npt.lamps trajectory rather than VT from before. And here we are outputting the mean square displacement. Whereas before in the restart file, we had the RDF. So mean square displacement is roughly, it's a measure of how much, it's a measure of how much particles move over the entire simulation. So what you do is you sort of do, you take the position of a particle at time t minus the position of a particle at time 0, you square that, and then you average that over all of the particles. And you end up with a function that shows you something that is very closely related to diffusion. I mean, it shows you how your particles diffuse out in the system on average. And actually, it is possible to use the mean square displacement and the slope of the mean square displacement to calculate the diffusion constant for your simulation. And this one, so like before, like with the RDF. There's a couple of further caveats for restart files. They heavily depend on CPU numbers. So yeah, that is a very good point. If you run a restart file and use a different number of CPUs, it'll probably crash. Which means that you can't create a restart file. Yeah, and also the CPU type matters. So you couldn't, because the architecture on ARCHER2 is going to be different from anything that you've got, probably in most other places, you wouldn't be able to just transfer a restart file from one place to the other and have it run. However, there is a non-binary file called a data file that you can output instead, and LAMMPS can read a data file, and they're because they're non-binary and because they don't define anything like the number of CPUs or things like that, you're able to transfer those a lot more easily. Thanks, Rui. Cool. So mean square displacement, it's a compute just like before. We give it a name. It's called MSD in this case. We're giving it a group, all particles. We want to calculate it for all particles, and then we define what compute we're using. In this case, it's MSD, and this doesn't take any other arguments, so it's quite an easy one to use. And then, just like with the RDF, we're using a fix, except instead of average time, we're doing average correlate because we're wanting the correlation of this function as opposed to the time averaged value of this function. The time averaged value of this function would be particularly of interest to us. But the rest of it looks exactly the same, or very close to the same. So you've got the name of this fix command, which particles you're using, the frequency at which you're doing it, how many time steps you're doing it, when you're going to stop. So basically, you're just calculating, or in this case, we're calculating this throughout the simulation. And here we're saying we only care about the fourth component of MSD. So compute MSD produces a, every time step will produce a vector with 4 entries. The first entry is diffusion in the x-axis, the second is diffusion in the y-axis, the third is diffusion in the z-axis, and the fourth is average diffusion across all axes. That's the one we care about, so let's just output that one. We're outputting it to msd_lj.out. We could have also put YAML before, and we want a running average of this. Yeah. So now, hopefully, if we run that, it'll just work. Should take about 15 seconds. Again, I hope you've been finding the exercises useful, the playing around with the input scripts and submission scripts useful in order to just get an idea of like how to do the test and how to run with LAMMPS. That's a bit longer than 30 seconds. Than 15 seconds. There we go. And now we have a file called msd, lj.out. Now, one of the quirks of some of the computes have certain quirks, and actually some of the fixes have certain quirks. And actually, the fix average, the fix average correlate has a very annoying quirk, which is that when you tell it, I want you to output this, it will output it at time step 0 and at whatever the final time step is. And if you had like a smaller value here than the total simulation time, then it, for every single multiple of this, it would output it, which can be really annoying to visualize because the way it does this is it outputs at time step 0. Well, nothing's moved at time step 0, so you've got a bunch of 0 entries. And once you get to 50,000, then it says, oh, okay, and at the end of the simulation, this is what it looks like. And we only care about the bit at the end of the simulation. So that's something to be aware of with this average correlate. And actually, this is true for all average correlates. If you're outputting more than once, so it will always automatically generate an output at the very start of the run. If you are outputting whatever value it is more than once throughout your run, it will just append it to that same file, which means if you naively go to plot this, let's increase that to, if you naively go to plot this, you end up with a plot like this, which looks terrible, right? You've got what you were actually looking for here is the top non-straight line, and then you've got this other straight line that just goes back to the origin. And what that is basically the first time step goes to 0, and then it shoots off to the final time step of the previous one and runs backwards, which is not really what you want. So there's 2 ways to go to get around this. The first one is you can say, well, okay, fine, I know I need to ignore that line. I guess you can also output with points instead, and then that's not point size. There we go. And then you get around that error, but then you've got really large points. Or what I suggest doing is just running a tail. So I'm taking the last 50,000 lines of that MSD file, outputting them to a new file called MSD final, and then I can new plot run that, and there it's no longer got the weird line. Now, the way that mean square displacement works is the very first point, time step 0. Well, that's done however many time steps there are in the simulation. Like, you can always know that time step 0, also it's always going to be 0 because at any given time step, a particle is at exactly the same position as it is on that very same time step. Then time step 1, well, you're able to average that a number of times equal to the number of time step total simulation runtime time steps minus 1, because you've got the difference between time step 1 and time step 2 is 1, but also the difference between time step 2 and time step 3 is also 1, and you can kind of do that over and over again throughout the simulation. And this kind of keeps, this idea keeps going until you get to the very final time step here, the time step 50,000 in this case, which there's only one shot at it because there's only one time where there are 5,000 time steps between the initial time step point and the final time point that you're trying to look at. So the error bar increases significantly. You should be aware that the error bar increases significantly as you go forward in time, as you go forward in the x-axis. But that's okay, because we're usually mainly interested in the bit here. So let's just zoom into, let's do this bit. Nice. That's still too big, so let's go there. There we go. So a couple of things about the mean square displacement. Actually, because this is a fluid, they all kind of always look the same in a fluid. What happens at first is the initial movement is quite slow because the particles are stuck within a ring of other particles that they need to jam out of before they can start really exploring space. And so you get this slow quadratic increase that then becomes linear. The quadratic increase is just breaking free of its initial neighbors. And then once you get to the linear region, well, that's in the diffusive regime. Actually, you can take the gradient of the linear region to work out the diffusion constant of your system. So that's one of the reasons why some people sometimes look at this. Yeah, so that's the mean square displacement. The one last thing I didn't do is if you look at, not final, let's look at LJ.out. You'll see that there are 4 entries. Entry 1 is which time step is this? So it's time step 1. Entry 2 is what's the difference between the time steps? So here the delta t is 0, delta t is 1 time step, all the way up to 50,000. How many times is this seen? It's seen 1, and then 0 for all the others. And then how many? What is the average distance that has been traveled? So this one's not particularly informative, but if we look at the final product, you'll see that there are 50,001 occurrences of 0 time steps because our simulation ran from time step 0 to time step 50,000. So that's 50,001. Where's that so high? Oh, it's because it's the wrong way around. Yeah. It does put things the wrong way around, which is a bit annoying. What is it? It's SD final that. Yeah. But yeah, so this has been seen. So I got it the wrong way around actually. This is time step 50,000 as far as it's aware. It's been seen 49,999 times. It's a delta of 2, and this is the distance in delta 2. So yeah, it's also outputs things the wrong way around, which is really annoying, but it's something to be aware of. But when you do get it to work, you're able to get something like the diffusion coefficient quite quickly. And actually, you can, within LAMMPS, write a script that will calculate the gradient for the diffusion coefficient for you. So that's mean square displacement and restart files and how to use them. One thing I will say, there's an optional exercise that you can do in your own time to, you can run something very similar to the mean square displacement. You can calculate the velocity or the correlation function using very similar steps to what we did for mean square displacement. And if you're interested in understanding the mechanisms, like what LAMMPS reads, what it's looking for, trying that is a really good idea. Now, the last bit of the section, we're going to be talking about variables and loops. So we've already talked about variables because we've been using one for density, but there's a couple of other ways, things that we can use, which again, we'd already talked about. The one I want to mention here is loops and indices, because loops and indices allow you to basically loop over numbers. Now, the difference between a loop and an index is a loop will loop over some integer number. So here, if you've got, for instance, variable a loop 10, it'll run something when a is equal to 1, then when a is equal to 2, then when a is equal to 3. I can't remember, it might be 0 indexed actually. So it might do a is equal to 0, then 1, then 2, then 3. And what it'll do is it'll do everything between this command and next a. Yeah. So yeah, fine, it's going to label the loop, then it's going to dump all of those things, then it's going to run that job, then it's going to dump, and then it's going to do the next a, and it's going to output everything in the correct file. Now, this particular loop is not is not terribly impressive. Oh, they're from 1, cool. Not 0, so it would go from 1 to 10 in this case. This loop isn't particularly impressive, but if, say, you wanted to run a simulation where you're incrementally increasing the temperature from, say, I don't know, 273 Kelvin to 293 Kelvin, and you wanted to run the simulation without having to just take a restart file and restart the simulation like that, well, you could use a variable to do that and incrementally increase the temperature. Indices are incredibly similar, except they can take strings instead of necessarily integers. So here you've got variable d running an index. It's gonna the first time that you run this, d is going to take the value run 1, then it's going to take the value run 2, then run 3, all the way up to run 8. And wherever d is called, like say here, where you've got the shell cd command, that is telling LAMMPS run this as if it is in a shell. So it allows you to put shell commands into your LAMMPS script. So in this case, go into this directory, then read this data, and then run that, and then go back out of this directory and do the next d. It's a way of making sure that your outputs, if you're doing multiple outputs, are in the right place, or if you've got multiple inputs, they're in the right place. Now, definitely with this particular example, there's other ways of doing it, but I'm sure you can imagine that there are situations where being able to have a variable that changes what the string is associated to it might be helpful to run your simulations faster. There is another exercise which, given the time, I will probably say we can do. I think it's a repeat of the one we did before. So I would probably say this is one that you can do in your own time. But at this point, are there any questions about anything that we've covered so far? Deafening silence. Cool. In which case, let's talk about some additional features. We've already talked about a few of them, like VMD, visual molecular dynamics, but there's a couple of others that we can talk about. If you have GPUs, you can compile LAMMPS to make use of those GPUs. And that can really accelerate your simulations. This is especially true if you're running anything with fast Fourier transforms. LAMMPS does a really good job of offloading its fast Fourier transforms, so it's long-range interactions onto GPUs. If you do, you can find how to compile with GPUs on the LAMMPS in the LAMMPS manual. If you're using one of our systems, so one of the systems that EPCC looks after is a system called Cirrus, which does have GPUs. If you're wanting to run LAMMPS on GPUs with Cirrus, we've got installation instructions. We're more than happy to share those with you. So please do get in touch and let us know if it's something you're interested in doing. Once you've got your GPU installation, you can use GPUs to accelerate. You can accelerate GPUs by running your LAMMPS job with the minus package GPU and then the number of GPUs you want to use. So it's possible to run LAMMPS on multiple GPUs rather than just one if you've got access to more than one GPU. Now, let's go on LAMMPS pair styles. Here we go. This should hopefully have a list of them. Yes, cool. If I control F GPU, does it show me these? Yeah. Do they come off, or is that just a list of the ones that have been? Yep, that doesn't tell you which ones. Oh, it doesn't have a nice easy way of checking. That's a bit annoying. Though I'm pretty sure if we just look in the source direction, we should be able to. You can always look into. You can always look into. I won't have the source file with it. Oh, it does. Excellent. There is a source file. SRC. That's not happy. Would it be? It could be. Cool. But anyways, I think I can't find an easy way of finding a list of which ones are GPU accelerated. However, if you click on any pair style, let's take the one we've been using, because I know that. We've been using LJ. If you look at LJ cut, it tells you there are variants such as LJ cut GPU, LJ cut Intel, LJ cut KK. Yeah, so if it's got a /GPU, then you can use the thing. Oh, Rui's found a list of all of the GPU things. Let's have a look. Here we go. So if they've got a G next to them here, they can be run on GPUs. So this one, Amoeba is, Borntan, Coulomb DSF can, and things like that. So there's a fair few of them. There's also some commands that can that are optimized for use on GPUs. And as Rui says, with each new version of LAMMPS, the number of these that are GPU enabled increases. Cool. One of the questions is, how is the dielectric constant calculated in LAMMPS, or is it assumed for the calculation of Coulombic forces, or is it assumed to be equal to the vacuum permittivity? Actually, you set your dielectric constant when you set your long-range interactions. From memory, but we can check that with oh, and you can also reset it with why is there in the PPPN? There should be a PPPN. Anyways, oh, it's because it's long, isn't it? It's evolved. Okay, there we go. Case-based style. So there is a dielectric command, as Rui says, and then some of the interactions will have a dielectric constant, or others will assume it's in a vacuum. Yeah. Cool. Back to GPUs very quickly. Well, it's not the right one. That's the right one. Yeah. So if you've built your version of LAMMPS with GPUs, you can use the LMP minus PK GPUs with the number of GPUs you want to run. Then you should add to your LAMMPS input script. Oh yeah, I'm not in the right place, am I? You should add to anything you want to optimize with GPUs the appropriate GPU command. Now, if you're feeling adventurous, you can use the -sf GPU flag, which will append the /GPU suffix to every single thing that has a GPU-enabled component. Yeah, I would say that this is at your own risk because it's not necessarily going to go faster on the GPU, so you probably want to test this. But yeah, I mean, in terms of how easy it is, if you wanted to take a job that we've run and make it entirely run on GPUs, your input script would go from something that looks like this to something that looks like this, with this added here to say you're running on one GPU, this added here to say that you want everything that's GPU enabled to be GPU enabled, and that's it. Everything else is the same. So we've already played around a bit with visual molecular dynamics. There are a ton of plugins for this that you can use, and you can build anything you want using the TK console, which I don't think I showed, but I can do real quick. I did actually accidentally show it, but let me get that across. And here's my little, there we go. If you go to extensions, TK console, just click that. It will open the TK console. There's no way for me to zoom in, unfortunately. I'm really sorry about that. But in here, you can run commands like ls, or you can run topo tools or things like that, and yeah, it'll tell you. You can select atoms, you can use that to prepare simulations, exit, things like that. Yeah, one of the main plugins for this is topo tools, and if you just Google topo tools, there's loads of instructions about what you can do on there, and yeah, there's loads of really handy options that you have on there, like, you know, to make your simulation look a bit better, to select certain parts of your simulation, to rewrite your simulation from this. Yeah, it's quite a handy tool. Actually, the people who develop visual molecular dynamics, I think, have very close links to the people who develop LAMMPS, and the person who's designed topo tools, Axel Kohlmeier, is one of the LAMMPS designers. There's some other software that might be of interest. Obito is an open source molecular dynamics Monte Carlo visualization tool. MD Analysis is a Python library that interfaces with molecular dynamics simulations for fast processing. There's a Python LAMMPS analysis tool called PyLapse. Did that used to be called PizzaPy?
I don't think it's the same thing. So PizzaPy was done by the LAMMPS developers. PizzaPy is still available, although it's Python 2 and it has never been ported. So while it can work, it can be a little bit of a pain to set up a Python 2 environment nowadays since it's been deprecated.
Yeah, makes sense. And then the final one, which I think Rui was going to show us how to use after we finish, for anyone who's interested, there's a software called PackMol, which is really helpful for creating and packing LAMMPS data files. So if you wanted to start a simulation and didn't want to have to hard code it in LAMMPS, because it can get quite messy, and actually you'll have noticed that for most of this session, we've not really looked at the in.ethanol because there are tons of details in there. Like, you know, when we're creating our region, we want to create our box and we need to define all of the angle types that we've got, all the dihedrals, the extra bonds per atom, specials per atom, things like that. And then we need to define all of our masses. There's way more atoms, so there's more masses to define, all of the charges and things like that. It very quickly becomes very big. There's another way of doing this, which is to create a simulation box with TOPO and then to use visual molecular dynamics to generate a LAMMPS data file that you can then read from.
Yeah, I can quickly show that. I grabbed some files that should allow us to quickly build box.
Yep. So what I was going to suggest, is how about we have it as an optional extra of like, we're basically 5 minutes away from the end of the course, and those who want to stay to learn about TOPO tools are welcome to stay, and those who either can't stay because they've got something on afterwards or because they're probably not going to use it don't have to stay. Does that work? Well, I'm not hearing a no. Cool. So next steps. First of all, well, thank you everyone who's made it through to this far in this course. I hope you found it interesting so far. This really is just like looking at just the first layer of LAMMPS. There's so much more that you can do with LAMMPS. There's so many more things that we could talk about, and it's always really hard to condense all of the information through a course like this. In terms of where you can go to next, well, you know, hopefully we've made it clear that in both Rui and my opinion, the LAMMPS manual is amazing, and everything that we've discussed, everything that we've described, usually when writing the material, we would look at what it is in the LAMMPS manual and then write it from there. So that's usually our go-to if we've got a problem, is it in the LAMMPS manual? There's also a number of handy how-to sections. So, you know, how to restart a simulation, all the way to how do you simulate it for P water. I think they've got some how to run with quantum espresso on there. Nope, apparently they don't. Cool. But yeah, so there's loads of how-to manuals. So check if what you're wanting to do is one of these, and that'll be a good first place to learn about how to do the specific thing you're after. Now, the LAMMPS example scripts, if you ever download LAMMPS, let's go back to here. If you ever download LAMMPS, it comes with an examples directory, and in there are tons of examples, such as, for instance, like colloids. Let's look at that one. Really, you're not muted. And there it comes with an input file, and yeah, it's just an input file from the LAMMPS developers that runs a simple colloid script. There's one called, I think, friction as well that you can do. They've got tons of them, and very often, I think it's if you search LAMMPS examples. Yeah, example script. It'll tell you what it's running with here. So here it's using the Axelrod Teller Muto potential. Here it's using the you know, it tells you a quick overview of what they are. So that's a really good and useful place to look. And then finally, if you still can't find the answer, there's the LAMMPS mailing list, where as a first thing, check whether your question's been asked. And if it hasn't been asked already, like, feel free to post it, and LAMMPS users and LAMMPS developers will help you and answer your questions. So that can be a really useful resource. Now, in terms of ARCHER2 resources, we will be, you're all part of the TA100 project. Now, under your TA100 account, you've got a small amount of budget. I think it's a couple of node hours, maybe 10 or 20, I can never remember. And we will leave this account open for you for a couple of months following the course. This is really to give you an idea that, this is to give you two things. The first one is it's to allow you to, if there's any bits of the material that we've covered today that you didn't quite understand or wanted to go over again, then you still have access to the course material and to the environment for which the course is designed, just to make sure that you really understand what you're trying to learn today. But the other one as well is for you to maybe try out some of the simulations that you're interested in and test how ARCHER2 works for you. Now, if you have any questions about using ARCHER2, the first place to go is always the ARCHER2 manual. We work pretty hard to make sure that the manual is informative and easy to use, including there's even a LAMMPS page which sort of tells you, well, here's how here's what we've included in the central install. There's a sample script and then a link to our building instructions for if you want to. So if you wanted to compile your own version, you can just go there. If you can't find the answer you're looking for about ARCHER2 in the ARCHER2 manual, please do let us know by contacting support@archer2.ac.uk. So the address right here, where we will be more than happy to help you. If this is related to this course, please mention that it's to do with this course, and then it'll get to either Rui or me to answer. Now, finally, the ARCHER2 training team runs a large amount of wide and varied training. We have a page on the ARCHER2 website where we sort of describe all of our training which is upcoming. So, for instance, what have we got coming up? It can range from things for, introductions. So, for instance, introduction to LAMMPS is green dot is for someone who's wanting to first learn something, has never really used LAMMPS. We've got intermediate courses like modern C++ for computational scientists. And then we've got advanced courses, so things like the efficient use of the HP Cray EX supercomputer. ARCHER2, that is very specifically for people who are really trying to get as much oomph as they can out of ARCHER2 to learn a bit more about that. All of our courses are free. A lot of our courses are online. You're welcome to register by using the register link. Some of them have waiting lists, which you're welcome to join. Yeah. The other thing that we offer is every single course we teach, including this one, it's not there yet, but it will be eventually. For every single course that we've taught, we keep all of the course material live, and we add the video recording of the lectures. So you know how I said that we were recording this lecture? It's because we will be adding this. So for instance, let's say you're interested in learning an introduction to OpenMP. You can click on there, and you get a page which is very similar to the one that you have for the LAMMPS course, with the course material, and all of the course material is there. Tells you what the breakdown of the thing was, what the lecture notes are. You can go through the course, and if you want as well, there's a link to every single YouTube page for YouTube video for all of the sessions. So you could watch the entire of that lecture and learn about the introduction to OpenMP. And this is true for the vast majority of our courses. We put recordings up online. Some of them we don't. So for instance, this one was done in person, so we didn't record it. Some of them we don't also because, well, we accidentally forgot not to press record, but most of them we do. Cool. So yeah, with that, that takes us to the end of this LAMMPS course. Please do let us know if there's anything that you wish we could have asked and you didn't have time to or didn't feel it was appropriate. Rui and I are going to stay around for a bit in order to answer any questions that you've got left. Rui's already doing that in the chat, I can see. After this course, probably today or tomorrow, you'll be receiving a link to a feedback page, and you'll be asked to provide feedback for this course. Please do let us know what you thought of the course, what you thought we did well, what you would have liked us to do better. That'll really help us know how we should improve this course going forward, and we appreciate all feedback that we get. So please do take the probably 30 seconds that it takes to fill out that form. Other than that, Rui and I will be staying around because for anyone who's interested in learning how to use PACMOL to prepare a system, by all means, please stay. Otherwise, this is the official end of the course. We will put a recording of the PACMOL bits up. It will be included in the recording, but this is the official end of the course. Thank you everyone for coming to this course. We really hope that you enjoyed it, and yeah, please do let us know if you've got any questions, and have fun using LAMMPS because it's a really fun, nifty little molecular dynamics software. Yeah. And I will hand over to Rui for PACMOL, and yeah, feel free to, if you're not that interested in PACMOL, not stick around. And if you are interested in PACMOL, do stick around.
Okay, I will share my screen. Okay, so the first thing I wanted to show you is that one of the pages in the LAMMPS manual is these auxiliary tools, and there's a load of tools here. Some of them I've not even ever seen. The one which I was trying to think of earlier that I couldn't is this multi-template one. And if you want to build anything that is complex in terms of structure, so you want to put a specific molecule here to build, imagine you want to build a string of DNA or anything like that, I think multi-template might be what you're looking for. It is complex, but it is incredibly powerful, and I would advise you to check it out. Just as an example, this is the kind of things that you can do with it. Just by defining some simple molecules and ions, you can then script it. I believe it uses a Python backend. You can script it to generate whatever kinds of systems you want. But then even from just moieties, parts of the molecule, you can generate polymers or anything like that, and all the way up to micelles, rings, and extremely complex structure like this bilipid layer. So it is an incredibly powerful tool. The other one, that if you're just wanting to generate random like an initial coordinates of a random sortation of molecules, and you want to mix several different types, for example, PACMOL is incredibly good at that, and it's much more simple to do. So if you search for PACMOL, you'll get to this website from the University of São Paulo in Brazil. And the number of commands that PACMOL has is quite small. I think it's 11 or 12 or something like that. And we can go through that very quickly, but they basically fall under the two categories: inside something or outside something, and then what is that something. So inside or outside a cube, then you have boxes, and that just means a rectangular prism. Then you have spheres, ellipsoids, and the planes. And cylinders. They've been increasing things. So most of the stuff I do is using inside boxes and using a fixed. Fixed just means don't move it. And with that, you can do most of the random generation of initial configuration of molecules or anything like that. You will need to give those commands to PACMOL. I tend to write them in a script, but you could type them all in the terminal if you wished. It has scripts don't tend to be very big, so this script generates a mixture of water and ethanol. Here at the start, you just define how big a distance you want between each atom. That's the tolerance. I believe that will be in angstrom. the output line is just the name of the file you want to write your output to, and then what file type you want to use. I do not remember exactly how many output file types PacMol supports, but at least PDB it does XYZ, and I'm sure there will be a few others. Then each of these structure sections is for a different type of molecule. So the first one you have here is just water, and if I show you what this XYZ file looks like, it's just the coordinates of one water molecule. It's a regular XYZ file that's used in all of chemistry. The same will be the case for that ethanol one. The second line here, number, is how many water molecules you want in your simulation, and then this is the command that tells PacMol how big of a box you want and where do you want to put the molecules. So it goes XYZ directions low and then XYZ high. So this means between coordinate 1181 and coordinate 7979 159, you can put 5,364 water molecules. I was doing a slab of water. I didn't want it in the beginning, but usually you'd start at the beginning of, at the origin, for example, something like that. The starting at 1 here is because if you have your atoms really close to the periodic boundary of a box, LAMMPS might throw a fit. So it is usually useful to keep that distance, to give that 1 angstrom buffer basically in between where you put your molecules in PacMol when you're building your data file and then when it's running LAMMPS. LAMMPS will then expand it to the actual box bounds that you give it. And then I just have a second structure section here for ethanol, 1,048 molecules of ethanol using the same coordinates basically. And if I give the command is this, PacMol, and then give it the input script, PacMol will start to generate XYZ file with the number of molecules that I told it to. And it is, if you don't try to compact it a lot, it can be quite quickly. So let me see if I can make VMD work here and show you just how that looks like. Might take a second for it to load. Let's see if we're successful or not. There we go. I'm not entirely sure that this is working 100%, but at least you can see that there are different kinds of molecules there, and they are colored differently. So the waters are the pink ones, and the blue ones will be the ethanol. So now you have an XYZ file. This is still an XYZ file. So if I show you what the file looks like, it's still just an XYZ file with a bunch of atoms in a row. So what we can do then is use the Tober tools in VMD to create a data file by bonding everything together. To use that, I have over time built a bunch of scripts, but the basics is that for each atom type that you have in your XYZ file, you want to select it and then give it information about what kind of atom that is. So you want to give it a mass, a type, a charge, an element, and a radius. The radius is what defines how big the bonds that VMD will create are, and these can be tricky to get right. But if you stick somewhere close to the regular chemistry radii, van der Waals radii, you should be fine. Unless you're trying to compact your box too much at the beginning. So what I just have here is just repeating these for all of the atoms, the atom types that I have in ethanol. If I show you that, so I have, this is the ethanol. The atom types are this 5, I believe, and I'm just selecting them with this first command in the line. I'm just atom select top. This is the topo tools command to select all the atoms that are named this, and then I'm adding all this information to those kinds of atoms. So the mass, the type, the charge, the radius, and the element. And I have the same for water. At the end, I'm also calculating some extra information that we can go through. To then use VMD to generate the data file from an XYZ file, then I'm just going to use the dispdev flag. This just means that tells VMD not to open graphical output, so it will be just on a terminal. But we can do, because I have all those commands in scripts, we can just run this directly from the terminal, and that means that VMD won't crash on me. It's always nice. So if I source both of my scripts, it will read all of those commands and execute them in order. And in the water one, because I have those extra lines at the end, it will calculate a lot of things for me. It calculates the names of the bond types that it has generated, and here is where you see if there's any bond that you shouldn't have. For example, if I had any of the ethanol atoms connected to any of the water atoms, I knew that would be a very big mistake. Then I have the same for angles and dihedrals, and then I have a nice list of just how many bonds, how many types of bonds, which is these 6 types, and the same for angles and dihedrals. So this information lets me know whether this is the expected number of bonds or not. So if you know how many bonds your one molecule of ethanol has multiplied by the total number of ethanol molecules you have plus the same for water, you know how many bonds you should have. And in some cases, if your radii are wrong, you can get mistakes here and get bonds where they shouldn't be, and then LAMMPS will complain and crash. And then using this topo command, after all of these bonds, angle, and data was generated, you can create a LAMMPS data file, and VMD will write that. Now, those commands here at the bottom are kind of important. So all of the topo tool commands start with topo. All of those are topo tool commands. So these topo bond type names just gives the names of the bond types, and the same for angles and dihedrals. The commands in topo are very systematic, let's say, and all of that information that I had, number of bonds and stuff like that, is all of these commands. The important bit that needs to generate your file is here. So you need to actually maybe doing this without all of this might be better. So I go here and I delete all of that. So you could do all this selection by hand, so these bits, but it is a lot and it's very repetitive. So I always suggest that you when you build your first molecule, you do this, and you can always just reuse it. So these package. I'm not going to remember the name. tuples. There you go. So if we source ethanol and water. Then there we go. So this first number was what VND naively thought the number of bonds were. But then if we use topo tools to recalculate the bonds using that data that we set up on the .tcl files, it then recalculates the number of bonds, and it's the 19,000, which is the correct number. And then we can tell topo to guess the angles and to guess the dihedrals. And from the bond information, it will do so correctly 99.9% of the time. And then it's contact names. Bonds. I'm not forgetting the commands. This is what happens when you don't use topo for about 2 months. And bond types, of course. That does not seem correct. That's correct. Well, something. So, in summary, this is a slightly complex problem and question, and PACMOL helps solve some of it, but you need to add the complexity of TCL tools or topo tools into it to have it. I will make these files available on the GitHub, maybe as an extra exercise or something, and I will write a description of what they do and where to find any more information about this. I'm happy to answer any questions about it as well, so do let me know. But as a demonstration, I think is what I was able to do.
Yeah, great. Thanks for that, Rui. And thanks also for agreeing to make this available to everyone. I guess this takes us to the end of this all-day course. We really hope that you enjoyed it. Please do let us know what you thought of it in the feedback, and I will stop the recording now. And if anyone has any questions that they didn't want to ask while we